Hello students, in this lecture we'll study Green's theorem. This Green's theorem we are not going to use anywhere at third year BSc, but it is there in the syllabus. We'll also study another function known as Dirac delta function. There are two Green's theorem, the Green's theorem in first form and Green's theorem in the second form. So let us try to obtain Green's theorem in the first form. So we use here a divergence theorem, which is surface integral of the function equal to the volume integral of the divergence of the function. On the left hand side of this divergence theorem, vector d sigma, we replace it by unit vector n cap into the magnitude of that vector d sigma. Now here the symbol n is used because the direction of the surface area is perpendicular to a point on the surface, that is normal. So that's why symbol n is used. Now let us substitute in this equation 1 the vector f equals psi grad phi. Psi and phi are the scalar function. So we substitute on the left hand side and we get the surface integral of psi grad phi dot n cap d psi d sigma, and on the right hand side the volume integral of divergence of psi grad phi dv. Then on the left hand side we use what we have studied in the directional derivatives. Here that dr in the directional derivative is replaced by vector n, and in the denominator the magnitude of that vector dr is replaced by n, and that is written as that del phi dot n cap, because vector n divided by n is n cap, and that is nothing but equal to the directional derivative of the function phi in direction of n. That is what it means. Then we substitute on the left hand side, and what we get is surface integral of psi dou phi by dou n d sigma. On the right hand side, in that first equation, del dot psi grad phi dv. So del is like a derivative, so it is derivative of two functions psi and grad phi, and we use the derivative of the product formula, which is the first function into derivative of the second function plus the derivative of the first function into second function. So what we get here is the first function is psi, and the derivative of the second function, derivative means del dot second function is grad of phi, plus the derivative of the first function, that is del psi dot the second function, which is grad phi. Then in the last step we replace this del dot del by del square, and what we obtain here in the last step is nothing but Green's theorem in the first form. Let us obtain Green's theorem in the second form. We first take the divergence of psi grad phi, that is del dot psi grad phi, and we use here the derivative of the product. See, del is a derivative. Product here of the two functions, one function is psi, other function is grad phi. So that is equal to the first function, that is psi, derivative of the second function, that is del dot grad phi, plus derivative of first function that is grad psi dot the second function, that is grad phi. Same way, we get equation 2 by taking del dot phi grad psi. Then subtract this two equation, that is equation 1 minus equation 2, that is subtract left hand side of the equation 1 and equation 2 and subtract right hand side of equation 1 and equation 2. And when you subtract the left hand side of the equation 1 and left hand side of the equation 2, what you get is del dot psi grad phi minus del dot phi grad psi. Then on the right hand side, see del in the first equation, the second term grad psi dot del phi is there, and in the equation 2, second term on the right hand side is grad phi dot grad psi. But the dot product is commutative, that is grad psi dot grad phi equal to grad phi dot grad psi. So when we subtract, it becomes, that cancels, and what remains there when you subtract the right hand sides of the two equation is the first term on the right hand side of the first equation, that is psi del dot grad phi, minus the first term on the right hand side of the second equation, that is phi del dot del psi. Then what we obtained here, we take del dot outside, it is common for both the terms on the left hand side. So what we get is del dot psi grad phi minus phi grad psi. Then on the right hand side, we replace del dot del by del square to obtain psi del square phi minus phi del square psi. Then take a volume integral on both the sides, you get this equation. Then on the left hand side, use the divergence theorem, and when you apply the divergence theorem on the left hand side, that volume integral of the function, divergence of the function, that is del dot, function is psi grad phi minus phi grad psi, is equal to surface integral of the function. So this volume integral of divergence of the function, we replace it by surface integral of the function. So function here is psi grad phi minus phi grad psi, and that vector d sigma is the increment which is to be there in any integrand. Then further we write vector d sigma by n cap d sigma as we have done while obtaining Green's theorem in the first form. Then this n dot n cap is taken inside to each term inside the bracket, and then we use a directional derivative as we have used in the Green's theorem in the first form, that del phi dot n cap is written as dou phi by dou n, and del psi dot n cap is written as dou psi by dou n. And what is finally obtained is the Green's theorem in the second form. There are many types of delta functions. One of them was given by theoretical physicist known as Dirac, and it is called as the Dirac delta function, and it is denoted by small delta of x. It is a function of x. It is defined as infinitely high, that means its value is infinite theoretically, practically very large, and infinitesimally narrow, that means it is, the width is such a small tending to 0, with unit area, and area of that is 1. And mathematically it is given as delta of x equal to 0 if x is not equal to 0, delta x equal to infinity if x equal to 0, and integral delta x dx, that is the total area of that graph, is 1. Let us consider first the ideal case, the graph of delta x against x. So for different values of x, the value of delta x is plotted. You find in this graph that at the origin it has a value and it is going up to infinity, and for all other values of x, delta x is 0. So delta x equal to 0 if x is not equal to 0, and delta x equal to infinity if x equal to 0. In practical case, that is the physical quantity in practice which exist, the graph is given here. Now here you will find that near the origin, here that this change in x is very small region around the origin, the value of delta x is very large, very large. But outside that, the delta x has no value, that is delta x is 0. And if you find the area of this graph what is drawn there, area which is enclosed within this region, it is equal to 1. And this is Dirac delta function. Dirac delta function is used to represent density of the point charge. Point charge means full charge is concentrated at one point, and that means the density of the charge is there at one point. Around that there is no density, so it can be represented by Dirac delta function. Sometime in the physics we call this thing as a singularity. So physical quantity which can exist at one single point and its value is very large, but at one point, and around that nowhere else that physical quantity is present. Now two of the important properties of Dirac delta function is, number one, delta of kx is equal to delta of x divided by modulus of k. Now from the first property we get a second property by giving the value of k equal to -1. So when k is -1, what we get is delta of minus x, and modulus of -1 is +1. So this right hand side become delta x. So these are the two important properties of Dirac delta function.